This is a proof for what we do with the exponents when taking an integral. The integral of x squared, the 2 becomes a 3, and then the 3 also comes down and becomes the denominator and a fraction of the x. So x squared becomes 1/3 x to the third. I'll show the proof of this. The first part of this is covered in calculus class. The rest of it I just came up with because I'm curious about this sort of thing, and so I figured it out, and I thought other people might be curious also. To take the integral means to get the area under a curve. We can't get the area normally like we would with a rectangle where we multiply x times y. So we do a bunch of small rectangles and add up all their areas. X squared equals y for a parabola, or x squared equals f of x is my example. We got x, we have y here, but this is also x squared. Because whatever x is, say it's 5, we square it and we get 25. So I'm gonna use x squared and x to keep the same variables. Add up all of our rectangles here. It's 1 over n of x from here to here, so that's 1/10 of x, 1/5 of x, 1/1000th of x, whatever. So from here to here is 1 over n of x, here to here is 1 over n of x, say 1/10 of x, whatever. That means this would be 1/10 of x, 1/10 of x. Then to go up, you have to square it. So here you have 2/10 of x squared, 3/10 of x squared, and that's how you get your y value. We multiply the x times the y of each rectangle. We get 1 over n of x for the x component, 1 over n of x quantity squared for the y component. That's for the first rectangle. The second one will be 1 over n of x. So 1/10 of x, for example. The y component will be 2/10 of x quantity squared. So here's the x component, here's the y component. Here's the first rectangle, then a plus, the second rectangle, and so on until we get to n over n of x quantity squared. We pull out our like terms, so this is just like basically high school algebra, just a little more complicated with the like terms. 1 over n of x and 1 over n of x quantity squared is the same in every term. Pull it out. N squared times n is n to the third. X squared times x is x to the third. That leaves us with 1 squared plus 2 squared plus 3 squared and on. The exponents here will always be 1 greater than the original exponent because the original exponent is a 2 for x squared. That means for our y component, we have squared. So n squared gives us the same exponent, but we multiply it by the x component because this is the y and that's the x component. So n squared times n will be n to the third. Same thing with x. X squared for your y component times the x for your x component gives you x to the third. So these exponents will always be 1 greater than your original exponent. And these exponents inside your terms here will always be the same as your original exponent right here. Because as you can see from the procedure, I just pulled out all the like terms, but the squared is still left. You can test this to make sure you pulled out your terms correctly. Take 2 squared, for example, multiply it by 1 over n cubed and x cubed, and you should get this right here. Here's a part for which I couldn't find a proof, but I could show a reasonable approximation. Take this 1 over n cubed times all of this. Ignore the x cubed for now. So 1 over n cubed times all of this. It will look like 1 over n cubed times the sum of n equals 1 of n squared. So this is n squared. This will be 1 squared plus 2 squared plus 3 squared all the way up to infinity. This will always equal 1/3, or this denominator will always be the same as your exponent right there. So we've shown how we got that exponent right there. Now we've shown how we got the denominator of this fraction. You can plug it in on a graphing calculator to get an example. So take n and make it 1,000, which means we have 1,000 little narrow rectangles here. So 1 over 1,000 cubed, sigma notation of n squared, and you'll get 1/3. I found out on my graphing calculator, you just have to make sure these terms match, because on my graphing calculator, the n pops up, but you have to go searching for n, because otherwise you want to use the x here, and then it doesn't work. So you can use x or n, but either way. So this term could be 1,000, 10,000, or even 50, and you'll get pretty close to 1/3. The same works no matter what your exponent. So if you have x to the third equals f of x, and you integrate that, your exponent here in the denominator will be 1 greater, just like I previously proved. And these exponents right here will be the same as your original exponent, 1 cubed plus 2 cubed, and so on. When you solve for this, say take 1,000 in your graphing calculator, 1 over 1,000 to the fourth, and then put 1,000 here, so n cubed, so it'll be 1 cubed plus 2 cubed plus 3 cubed, all the way up to 1,000, you'll get 1/4. The denominator will always match the exponent of this term right here in the denominator. So it works for x to the fifth, x to the sixth. Just raise your exponent by 1, and then put that exponent in the denominator. So now I've shown how we got all of this. Let's take this times this. So it'll be this times the sigma notation of that. This comes down to here. This becomes 1/3, as I just showed. And this x to the third, just bring it down right there. I really wish I could have a proof for that, for this whole term here and here equaling 1/3, but I couldn't come up with one. I'm not a mathematician. I just do this as a hobby. So now I've shown how when you take the integral of x squared, you're going to get 1/3 x to the third. Add the c here for your constant, just to make it official. And I'm going to cover what the c does here as well, because I don't do calculus a whole lot, and I figure months or years from now, I may forget that. So I'm going to show why we have that c. I'm just going to pretend that the c is a 5 for my constant. And because an integral is just an antiderivative, so when you take the derivative of this, you bring your 3 down, and you get x squared. Then I'll bring this whole thing over here and take the derivative of all of this. Bring the 3 down, and you get x. You'll get x squared plus 5. 5 is the same thing as 5 times x to the 0, because anything to the 0 power is 1. When you take the derivative of this, you bring your 0 down, and this whole thing becomes 0. So that's why we add the c, because an integral is an antiderivative. And that's it.